Hello. So we're back, and today we will do a mixture of topics. Before we get on to dimensionless numbers and similarity and everything, I thought I would go over a few aspects of some of the things we've done before. In particular, we will look at, we very briefly introduced the energy equation. You remember we talked about the energy equation when we finished the last time, and our main focus there was to look at viscosity and figure out that the dissipated energy density went as mu, say this kind of thing, right? Where we really have dui dxj plus duj dxi, that kind of thing, right? But this was the main focus, and this was the coefficient of viscosity. The dimensions of which are grams, like so. Okay, so sometimes they call this a coefficient of dynamic viscosity, and you'll see, but keeping the dimensions in mind is very useful. So, so this was the main focus of what we did last time, and what we will do today is maybe write down. We also remarked that we already had seen the energy equation in a slightly different guise in the form of a Bernoulli constant, where you remember this, right? So the Bernoulli constant which is something like 1/2 u squared plus constant. This is true, however, only for a streamline, and it's true for irrotational inviscid flow, right? And this is not the velocity potential, this is the gravitational potential. Please keep this in mind, right? This is also a statement of energy conservation along a streamline. But what we will do today, so we along a streamline. So we said these two things. I just wanted to recap. What we will do today is try to write down an energy equation in the conservative form, just like we've written down, the other equations in conservative form, mass conservation, momentum conservation, and so on and so forth. So before that, just to recap, the conservative form of writing down any conservation equation is partial time derivative, which means that the moment you see these kinds of partial time derivatives, you are in the lab frame, right, of the density of whatever quantity you're talking about. If you're talking about mass conservation, it's mass density, right, plus divergence of the flux of this quantity is equal to 0, right. So suppose this was mass density, you would have and the flux of mass is, right. And if this was momentum density, you would have dt like that. This would be momentum density, and the flux of momentum density. Now this is divergence. Essentially what we're writing here is divergence, rho. We sometimes wrote this as an outer product. This is the same thing, is equal to, if we neglect if we neglect note, right. So, this would be the gradient of the pressure and this would be any external body forces. So, this would be the conservative form of the momentum continuity equation. Okay, this is the conservative form, and same thing. So, this would be 0 as such, and you would be able to do that. You would be able to write down the right hand side as 0 as long as you were able to pull this term in here, and this could be written as the gradient of a potential, in which case you could write it down exactly in the same form as this, exactly in this form, to be precise, exactly in this form. Okay. Now, in a very similar fashion, let's try to write down the energy equation in conservative form, simply by analogy with these other equations. It's useful in conservative form. But neglecting viscosity. For the time being, at least for writing it down like this, I don't want to be bothered about viscosity, about viscous dissipation. This is what we focused on the last time, but for now, in order to write down the energy equation in a neat form, I would much rather neglect viscosity, knowing fully well that if I wanted to add viscosity, I would simply write this down on the right hand side. That is it, really. So, in exactly going by this analogy, I can write down the conservative form of the energy equation as energy density. This is what I am going to write down now, right. So, I would write this, right, of the flux of the same quantity if I wanted to. I could also add I'll tell you what this means, and like this. Okay, this is the energy equation in conservative form. So clearly, what I'm implying by this is that this is the energy density, and because I've got a u here, this is the flux of the energy density, and this is another thing that we will come to in a second, right. Now, what I'm really saying by writing this down is that this quantity W that I wrote here, is W is the enthalpy per gram or per unit mass, and this is equal to the internal energy plus P over rho. This would be the internal energy of the gas. Depending upon how many ever degrees of freedom it has, you would have the formula would differ slightly. So, this is the enthalpy per gram. You can think of this entire thing as something internal to the gas, right. So, that would be this. Okay. So, this is the internal energy right here, and this guy is the kinetic energy density of the fluid. Okay. So, you can see how I'm able to how I'm able to simply write down the energy equation just like that, simply knowing simply going by the general form of going by this general form. Okay. Now, coming to right. So the other thing to keep in mind is that, so going by the same token, the quantity rho u times 1/2 u squared plus enthalpy density, yeah, minus, sorry, this should not have this is just a coefficient. This entire thing is the energy flux. Again, this is nothing new, right? So this has to do with the kinetic energy of the bulk flow, and this has to do with whatever is internal to the fluid. Remember, the enthalpy is this, and this quantity that we've written anew, the T is the temperature, okay, and you would be relating T to pressure and density using maybe a P equals NKT, P equals this kind of a formula. So this would be the gradient of temperature, and this would be the conductivity. So energy can be carried, can be transported due to temperature gradients as well. You may or may not want to have this, okay, and if you have this, then you need an equation of state like so, okay, because that's yet one more variable. You only have 3 equations, and there's one more variable, so you need to tie things together, right? So this is all I really wanted to say at this point. It's possible to write down an energy equation in a conservative form, in a form like this, and that is this. Yeah, it does not include viscous dissipation. If you wanted to include viscous dissipation, you would do so on the right hand side here. Yeah, it does not include other forms of energy generation. For instance, suppose this was a flow of chemical. So suppose there were chemical reactions as the fluid was flowing. There were exothermic reactions. That too, that's not a dissipation, that's a generation of energy, and you will be able to account for that on the right hand side just like that. Okay, just like you were wanted to include viscous dissipation, you would do the same thing on the right hand side. Okay, so that's it really. This is yet another way of writing down the energy equation. Okay. So I wanted to focus a little and one final thing before we leave this topic. Oftentimes in astrophysics, since this course is oriented towards astrophysical settings, we don't appeal to an explicit energy equation of the form that we just wrote down. Instead, we just use something like P equals, now this K is not the same as the other K that appeared in the conductivity, where this would be an adiabatic index. And I deliberately write down the adiabatic in quotes to imply that this need not be always 5/3 for always 1 as would be for a isothermal gas. It can be anything in between. But the point is, you can relate temperature and never mind temperature for the time being. We're not introducing temperature. We can relate pressure and density like this. In which case, you eliminate the actual need for an explicit energy equation, and everything, all the information about the evolution of energy is enclosed in this index right here. Okay, and if gamma equal to 5/3. Adiabatic, in other words, the system is closed and any PDV work that you do appears in internal energy and vice versa. And if gamma is 1, then it's isothermal. And in principle, it can be anything in between. And it's this gamma which tells you everything about the energy processes, energy dissipation processes. So many times, in astrophysics, as I said, we don't really appeal to an explicit energy equation. Instead, we use something like this, and it's just the way people do things. It's cheap. You can call this a cheap energy equation instead of writing down an explicit energy equation. I get away. Well, from a mathematical point of view, you can see if you tie down these two variables like this, there's no scope to have one more equation, like an explicit energy equation. Otherwise, you would be over-determining things. So that's one way of looking at it. The other way of looking at it is all the physics of energy dissipation or generation or whatever is hidden in this index right here. So this would be a polytropic law, as you know, and the polytropic index, I should not call it an adiabatic index, I should call it a polytropic index, because that's what's used in the literature many times. So the only thing is, often it's the polytropic index is not denoted by gamma, it's denoted by n. Okay, so like so. So all the physics of energy generation or dissipation or what have you is encapsulated in this polytropic index, right? So that's that for the energy equation, and I thought I would next start talking about, this was kind of where we wrapped up the last time, and the next thing I want to start talking about is go back to the Navier-Stokes equation, right, and talk a little bit about boundary conditions. How the inclusion of the viscous term, now we go back to viscosity again, and how the inclusion of the viscous term alters things greatly, especially with regard to boundary conditions. So we'll stop here for the time being. Thank you.